Stoichiometry, one of my all-time favorite things. Hi, I'm Sarah. I've been a math and science teacher for 20 years, and I enjoy making math engaging and fun for everybody. If you want tutoring, micro-tutoring, Cameo, click the link and do the stuff. Stoichiometry and chemistry when I was in high school were really, really, really difficult for me. I just had such a hard time, keeping it straight and knowing what was going on and how it was supposed to work, and it did not click for me until I got to college. So I muddled through somehow in high school. Not really sure how I know how I graduated, but I'm not really sure how I pulled out my grade in chemistry and then continued to be a biochem major in college. It was not at all what I expected. So stoichiometry is a lot of chemical unit conversions. Okay, so there's such a thing called a mole, which is 6.02. It's based on Avogadro's number, which I believe is 6.02 times 10 to the 23rd. So October 23rd is mole day, and I was so sad that my daughter was born on October 22nd. Because I was like, man, if it had just been one more day, it would have been mole day. But I was already 11 days overdue, so I got over it pretty quick. But yeah, I was so sad. So it's based on it's sort of like a dozen, right? So a dozen is 12, right? A mole, which is a number of molecules, one mole is this many molecules. And each element and compound and mixture and all those, well, not mixture, but each element and compound has its own molar mass, okay? So its own molar mass, which means it's how much does one mole of that substance weigh? Right? What's the mass of one mole of that substance? So if you think about it, if I've got 6.02 times 10 to the 23rd, 6.02 times 10 to the 23rd, if I have that many helium molecules, they are not going to weigh as much as that many iron molecules, right? We've got iron and we've got helium. These are two very different elements, right? So if I've got that many, so it's kind of like what weighs more? Well, nope. I almost said the wrong thing. So what weighs more, a dozen bowling balls or a dozen feathers? The bowling balls will weigh more, right? Because they're made up of different, each individual bowling ball is going to weigh more, right? So I have the same number of them, but I don't have the same mass of them. What I almost said was what weighs more, like a ton of bowling balls or a ton of feathers. They weigh the same. But the difference there is the number of feathers and the number of bowling balls, right? We've got the 6.02 times 10 to the 23rd. So this, like I said, this is the number of moles that are in, these are the number of molecules that are in one mole of the substance. Okay, so when you're talking about this, when you're talking about getting into stoichiometry, you're gonna go into converting, because it's really hard to measure moles, right? We don't have something that will go through and count molecules because they're really tiny, right? So what we do is we have to rely on the molar mass of knowing how much something weighs in order to get the right concentrations and things like that. Because when you're talking about a chemical reaction, the chemical reaction is based on the number of molecules that are there, right? If you run out of molecules to cause the reaction, then the reaction's going to stop, right? It's not going to keep going. So let me pull up just an example problem. Let's see. I'll just work through it. So we're looking at we've got the reactants and the products, right? You have the reactants that are going to react together, and then it's going to produce these products. So the question is how much of each reactant do I need in order for this particular reaction to take place, right? So for example, okay, if I've got an equation, so here's a balanced chemical equation for the synthesis of ammonia. There we go. All right, so we've got N2 plus 3H2 goes to 2NH3. So what this means is if I take 1 mole, so it's a 1 to 3 that's going to produce 2. Okay, so I've got 1 mole nitrogen, 3 moles hydrogen, produces 2 moles of ammonia. So that's what we've got going on here. So what I need to do is, let's say if I have, what did it say? It say 12 milligrams, 15 moles. Okay. The question that I found on here is how many grams can be produced from 12 moles of H2. Okay. So that's what we're looking at. So how many grams of ammonia can be produced from 12 moles of H2? Let's see. I need to figure out a couple of things. I need to figure out the molar mass of NH3, and I do that by looking at my periodic table. Okay, so I've got to pull up my periodic table. And what I look at is I've got the 3 hydrogens plus the 1 nitrogen. Okay, so that comes out to be about 17.03. So NH3 is 17, we'll call it 17.03 grams per mole. So what that means is if I measure out 17 grams of NH3, that is a mole. That is 1 mole, okay? So if I measure out 17.03 grams, I have 1 mole, because that's how much 1 mole weighs. Now what I'm looking at is when I look at these molecular numbers here, like 2 and 3 and 1, that's how many moles, that's the proportion, that's the relationship, okay? So if I've got 12 moles of H2, so each hydrogen atom is about 1. So I'm going to call the molar mass of H2. I'm just going to say H2 is 2 grams. So again, right, what weighs more, a mole of hydrogen or a mole of ammonia? Well, the ammonia is much heavier, right? We've got H2 here, we've got NH3 here, and again, NH3 is the ammonia, H2 is hydrogen gas. So let's see, all right, how many grams of ammonia can be produced from 12 moles of H2? Okay, so we've got what we're going to start with, and we know what we want to end with, okay? And we're going to use all these different relationships to relate them to each other, and we're going to use something called fence posting, okay? So I'm going to start with 12 moles of H2. I'm going to change my color. I'm going to use orange. I like how the orange looks up on the board. So we're starting out with 12 moles of H2. This is setting it up. This is setting up in a way called fence posting. So fence posting is just a way of setting up all of these different things. And what we're going to keep an eye out on is we are going to keep an eye on the units. We want to make sure that we can cancel out all the units, okay? So our bridge between the two things, we want to go from moles of H2 to grams of NH3. This is how we're going to join them together, is the fact that we use 3 moles of H2 to produce 2 moles of NH3. Okay? You don't really like chemistry, Peter. Neither did I. Neither did I. I did not like chemistry at all. And then once I realized that it was basically like all math and then you could like make cool reactions, I like it now. If you think about it as just like applied math, it's wonderful. Okay? All right, so 12 moles of H2. So I've got moles of H2 up here. So I need to cancel those out down here, right? So what I know is I know that 3 moles of H2 yields 2 moles of NH3. That is their relationship, right? And I got that from my equation, okay? So this 2 to 3 ratio comes from here, okay? So now, if I keep an eye on my units, right? Moles H2, moles H2, moles H2, moles H2, those are going to cancel out, okay? So now we're just at moles of NH3. But I don't want to get to moles of NH3. I want to get to grams of NH3. So now I've got, luckily, I know how many grams are in 1 mole. So I put 1 mole of NH3 down here. So 1 mole NH3. And 1 mole of NH3 is the same thing as 17.03 grams. 17.03 grams of NH3. Okay, now this is the really fun part. So now I get to cancel everything out. Ha-ha! So I take mole H2 over mole H2, get out of there. You're canceled. Mole NH3 over mole NH3, get out of there. Canceled. So all I'm left with is grams of NH3. So now what I need to do is I'm going to multiply across the top, multiply across the bottom, and divide. Okay, so I'm gonna get, let's see, I've got 12 times 2 times 17.03, execute. So 408.72. So I have 408.72 over 3 times 1, which is just 3. I'm going to divide by 3, and I get 136.24 grams of NH3. Okay. So I know that's chemistry, but it's still math. Yes, there are other factors. So that's the reason why I said it can be produced, right? There are lots of other things that go into this, like limiting reagents, right? Activators, temperature, all of those types of things. This is in a perfect reaction, right? With unlimited nitrogen, right? With unlimited nitrogen, how much could you make? You could make 136.24 grams of NH3 from 12 moles of H2. You can, right? Now, will you actually get that yield? Probably not, right? There's a lot of other stuff that goes through it, and that's a big part of organic chemistry when you're in college or in high school too, is looking at how much yield do you actually get. So you usually like calculate the ideal yield, and then you have to see how much you actually make, and it's usually kind of a depressing percentage, but sometimes you get really, really high, which is fun. It's mathed up.